thanks for the one. Yes, I really enjoyed meeting the new people and old friends and all the conversation that I had. This is my first time in Austria, and it's everything. And I got that. Also, I want to apologize. Maybe this title is a little too grand. After I attended the conference, I realized, as is the photo behind it. So adjusted title is over here. So in this talk, I'm mainly going to be talking about sublinearly Morse boundary, which is something that's been around for 3 or 4 years now, and introduce the main properties. And the newest theorem I want to end on is talking about its SB invariance property. Okay, so let's begin at the beginning. If this can move. Okay. So all of this work, all of the boundaries you've heard, some of them throughout the week, are all inspired by some Gromov boundary for hyperbolic groups. And there are kind of many other ways aside from consider the space law directions to give a compactification. But for us, this will still be our main focus, is to consider the most geometric or the most visual approach, at least for the beginning. So as a review, what do we have for Gromov boundary? And the reason that it worked out for so many arguments is that let's begin by let X be a telegraph of hyperbolic groups and fix a base point once and for all. And let elements of the boundary be infinite quasi-geodesic rates. You can say geodesic rates, it turns out to be not much of a difference, emanating from the base point. And then we create, so later gives us all the directions. And then we create equivalence classes, like get rid of the overcounting. If two of them are fellow traveling for an infinite amount of time, then they're considered pointing to the same direction. And then we give it a cone topology, such that the neighborhood bases are all the directions that at least after distance r, after radius r, still epsilon close together. So this setup is something we're going to try to mimic. This topological space is a Gromov boundary of G. So I'll be here most of the time for this reason. So because the motivation comes from a study of groups, so one of which is that we want it to be not so generating set dependent. So a generating set change will induce a quasi-symmetry on the telegraph. So quasi-symmetry invariance would be nice. And this turned out to have that property. The boundary itself is also compact and metrizable. And it does give a lot of a variety of topological spaces. There are the simplest examples. And where on the left, if you look at the hyperbolic plane or the associated groups, then you get S1 as the boundary, connected and everything. And on the right, you get a totally disconnected space that is a Cantor set. Okay, so that's all I'm going to say for that. And for all the applications, all the good stuff, you can look up all the work for the last 30 years in surveys. But because it has been proven to be so powerful, we do wanted to generalize and go forward and see, can we take the general guiding philosophy and make it more broadly applicable. So the guiding philosophy is, look, consider all the geodesic grids. So we first do that. Again, it's the base point. And look at all the geodesic grids emanating from the base point and collect them, use fellow traveling equivalence class, use cone topology, and just see what we get. The resulting object is visual boundary. It's called visual boundary. So visual boundary of R2 would be a sphere. Visual boundary of the Cantor set is still of the F2 is still Cantor set. So since it feels very nice, and it also generates lots of good results. But one interesting and somewhat stimulating result is by Croken Planner about 20 years ago. They showed that this is not a group invariant. So while it's very nice from a geometric point of view, but it is a little too wobbly. And then there are other results to say that it's not only it has more than one boundary, it's uncontained any boundaries if you just change local quasi-symmetry a little bit. And in fact, it's equivalently not group invariant. So even if you just do quasi-symmetry based on generating set change, you will still it would not induce so it's definitely not suitable for that particular purpose. So then when you consider, if you look at this example, you may realize that the things that's causing a lot of problem because some of these rays are going through a large amount of flats. And so they behave not at all like geodesics and hyperbolic space. So now we hopefully, so then Charlie Salter in importance created what's called the Morse boundary. So the Morse boundary in that picture would be trying to go through just the values. And this is in fact a lot of the math in the park. If you just figure out all the values are and follow them, you probably won't be lost too far. So this Morse boundary also tells us what are the hyperbolic directions of the space. And let us study the space, study the group in that way. So for review, and especially so if you attended a lot of previous talks, let's recall what a Morse boundary is. Morse direction, so we're going to build based on that by just adding a word here and there. So let gamma be a quasi-geodesic ray emanating from the base point, and then proper geodesic space, general geodesic space. A quasi-geodesic ray is Morse if there is a gauge function that quantifies, that specifies the state of the neighborhood, such that any QQ quasi-geodesic segment, the orange line, the alpha line, whose endpoints are on gamma, would force to be staying inside this MQQ neighborhood. So it says something like fellow travel implies uniform fellow travel. And then the definition itself seems like it will be the mixed quasi-invariance much more straightforward. And also has generated a flutter of studies since then. So the very good thing about it is quanti-isometry invariant. And also it's a visibility. What that means is that given 2 points in this boundary, there exists an actual geodesic line whose one side and the other hand limiting to those 2 points, so connecting them. And this is true for Gromov hyperbolic space, and it aids you in if you wanted to go further and try to work on rigidity problems. It's not compact because we selected the directions that are nice, that helps us. It's not metrizable in issue with the direct limit topology, and it's made metrizable by the Cashman-K topology constructed a few years ago. And the last thing is from the random walk point of view, it's not generic. So typical sentence has not converged to one of these points. So the question is, can we learn what we learned from this and find something larger? Okay. So this is what we're going to do 5 or 6 times in the rest of this talk, which I call sublinearification. So the idea is that geodesic ray or quasi-geodesic is an object that travels at a linear speed away from us. So if there's a bound error, as Gromov has just pointed out, then it doesn't matter so much in a coarse geometry asymptotic point of view. But it's conceivable that a sublinear error would also play that role in a lot of the not only viewpoints but actual proof may go through, and this is the case. So fix the sublinear function kappa of t for each boundary. So each boundary is associated with a kappa. Sublinear means if you take the limit as t goes to infinity, you get 0. In reality, if you have anything like this, you can do a little bit of technical work to make it connected and convex, but otherwise continuous and convex. But otherwise, you can start with anything. So first, I'm going to specify a neighborhood shape is exactly the shape of kappa, and that eventually let the norm of x be this distance to the origin. I want to select all the points whose distance to gamma is bounded above by some constant times kappa of the norm. Okay, so if n equals 1, I get exactly kappa neighborhood. If n equals 2, I get a sticker, but it's actually the same shape, so on and so forth. So the multiplication constant is just to make it bigger and bigger, but the shape is specified by kappa. So any kappa neighborhood is referred to any one of these, and it's notated by just gamma and the thickness only with the multiplicative constant. Okay. So just to, because I'm working with slides, I copied it over so we don't forget easily. The rest of it seems natural to us that now I wanted to find again, a family of gauges, but those gauges are explicitly just the multiplicative constant. And then I want to say for each QQ, there exists a bound only depending on QQ such that all the QQ segments with starting and ending on it should stay within the correct neighborhood. And if a quasi-geodetic ray satisfies this property, then I call it Kappa-Morse geodesic. So now I wanted to convince you that these things do exist, and there are a lot of them. And the toy example is this red geodesic ray in this tree of flats, which you've seen several times by now in some of the relevant talks. That spends what goes one step in the first flat, go up to the second floor, 2 steps, and then go up to the third floor and 3 steps, so on and so forth. So it has kind of a arithmetic progression. But why is this sublinearly Morse? Because any segment that wants to start and end on the red ray, because this space has so many touch points, the quasi-geodesic segments actually have to roughly follow the same itinerary. It is not so connected enough such that you can come back later. So it has to, even if you're bounded off on some other flat, it has to eventually come back. So it roughly stays along the same itinerary with some constants. If it does that, then bounded by bounded coset penetration property, the orange line, which you have to imagine, the line segment has to enter and exit each flat very close to where the red line enter and exit. So if that's the case, then it can only stray far away as far as how much two things can stray far away in a flat with boundedly close starting and ending point. And that is linearly, that is a linear upper bound. So in the second flat, the orange segment can leave, the distance to the red should be a multiple of 2, and the third one is a multiple of 3, so on and so forth. Therefore, this particular quasi-geodesic, the thickness in the neighborhood of the end flat should be linear with respect to n. But what is that a function of the norm? For any point in those neighborhoods, a measured distance to the origin is 1 plus 2 plus 3 plus all the vertical edges. Then that's roughly n squared. So if I pick kappa to be square root of t, this is definitely an element in the kappa boundary. And also, if my itinerary is 2, 4, 6, right? 2, 4, 6, 8, or 2, 6, 9, 12, or any other progression. So usually you can see there's probably many starting at this particular level with this particular pattern. In fact, there's a lot of them. So they do exist, and not all of them, and most of them are not Morse. Because Morse in that particular example would mean you spend bounded amount of time in each flat. So equivalence classes, we wanted to again push the sublinear computation forward and say, we say 2 of these are sublinear to fellow travel if they roughly sublinear to fellow travel. If when they intersect the ball, when they exit the ball radius r, their distance should be sublinear with respect to r. R goes to infinity. So that may seem like you're grouping together too many directions, which is not the case. But also, that is a good equivalence class for this boundary because we show that just the sentence that I said, fellow travel implies uniform fellow travel. So this is also sublinear fellow travel implies uniform sublinear fellow travel. So that way we're not combining many things. If a quasi-geodesic ray ends them, sublinear fellow travel and with any function are kappa-Morse ray, then that object itself is also forced to be kappa-Morse, and they fellow travel each other. And therefore the equivalence relations are defined by sublinear fellow travel. That is and the topology is also, if you attended the talk this morning, the topology is also created with exactly the same concept that is a very visual, it's a cone topology. If we, in fact, we wanted to take strictly just the visual boundary, the subsequent time from the visual boundary on the geodesics. But as Patterson proved out, their various counterexamples show that it does not produce the QI-invariant space. And the reason for that is if you only check geodesic rays, their quasi-geodesic rays can accidentally actually be wandering too far apart. So the point one is limited is different depending on which you travel. And the point of coarse topology, coarse metric, we don't differentiate geodesic, quasi-geodesic so much. Shouldn't have a. So what we should say is that all the geodesics fellow travel or have this cone requirement. All the quasi-geodesics for their respective tier also have this cone requirement, so on and so forth. If every layer of quasi-geodesic have this cone, satisfy this cone requirement, then this particular element is in the neighborhood of some quasi-geodesics. So that is to say, U, gamma, R, these are the base neighborhood bases surrounding gamma, which is quasi-geodesic, for any distance R. If for any other representative in beta, in B, sorry, beta in B, then I want to say beta restricted to R, so inside R, should fit under the Morse gauge of the central element gamma. So inside, if you only look at R, you couldn't tell that it was a different class. It acts still like the class of the central element, which is in philosophy this morning. And I added here that MQQ doesn't have to check all QQ until the end of time, because you don't have that much time, but also because we only care about the one up to R. Once it's bigger than R, this limit is meaningless, although it properties too. Good. Okay, so those are the tools that we need to assemble together. And with all that put together, we can say that let X be proper geodesic metric space. For a fixed kappa, the kappa boundary is the topological space that is invariant of quasi-symmetry and metrizable. For a larger kappa, that will be containing the smaller kappa boundary as a subspace, and the larger one and larger one. The union of all of them is also QI-invariant and metrizable. But in particular, this applied to group say this group now has an invariant QI-invariant boundary that is metrizable associated to each kappa. So you can choose different kappa depending on what you want to do with it. The properties of kappa of the boundary, I wanted to highlight that it seems to be very large from a couple point of views of largeness. In the sense that we can prove that, we can show that the sublinear Morse directions are generic, at least from all of the talks on random walks, from that point of view that we're talking about, and then Patterson Sullivan. So in particular, let G be a relative hyperbolic group or mapping class group, or more extended HHG. And let mu be a probability measure with finite support generated at the semi-group. Then you can pick kappa at least the log of t, but you can also pick it to be anything larger. And the choice of kappa, the whole, if you add a constant in the front, that doesn't affect the choice of kappa. The kappa to define the type of function. Then almost every sample path converges to a point in this boundary, and the kappa Morse boundary is the model for the Poisson boundary. And when you use a hidden measure associated to the random walk. So this builds on a lot of work has done previously, or this exploration has done many other work, including Patterson Sullivan, Bowditch, Kamenovich is the one who proved it for hyperbolic group in the third grade. Kamenovich later, Tyrrell, Mateus, and Gekman Yang, her so on, but then probably missing many other things. But I think from math class group, and this is the first one that is directly built on the boundary of the kilograph. That is QI-invariant. And for relative hyperbolic group, also the canonical geometric construction. So for this might make it easier to compare now which measure is similar to which, and so on and so forth. If we have a uniform topological space for them one. And also similarly, the characteristic is not in that, at least was not in that category of spaces because it didn't have or doesn't have a overall tree-like property, which I cannot get into. But we can also show using other tools that K0 spaces also have this. The Patterson Sullivan measure putting on the visual boundary of K0 groups. In this sense, a direction is also a sublinear Morse direction is also generic under this mesh. And we can show this also for your techno space, the boundary techno space. Okay, so to summarize, that we do have an object that is QI-invariant, topological space metrizable. It's not compact and it's large enough so that it can see really a lot of different dimensions. If I were to give this talk earlier, I would say that the part 2 will come after, but it already happened this morning, so that we'll make an attempt to compactify. But I'll move forward anyway to with my sublinearity. So this part of work is joint work with Gabriel Hallier. Who's also creating a permanent job somewhere. Okay. So if we agree with the philosophy that sublinear error sometimes can be absorbed, then we try, you can try it out even on the map itself. So extend QI to SVE, which stands for sublinear bilipschitz equivalence. So the definition of SVE is very straightforward with a set of properties and geodesic metric space. Given an entry point, I perturb the distance by some constant, the bound long-different constant. And instead of additive constant, I let the additive constant now become a function. So a sublinear function that should independently, that is based on the norm of x1 or x2. So if you have the map between two spaces that satisfy this relation, and the image, every point is close to some point, sublinearly close to some point in the image, then we choose these two, we say these two spaces are sublinear bilipschitz equivalent. I learned about this from first from Abdul, but then from Gabriel. So for people who are classically interested in it, I think they were interested in quasi-symmetric type of simply continual potential groups. But even for hyperbolic groups, there's a lot to, it turns out to be very interesting, there's a lot to say. For example, let phi be an SVE between the k-graphs of two groups. If one of them is Gromov hyperbolic, then the other one is Gromov hyperbolic. So that is to say Gromov hyperbolicity will survive is SVE invariant. And this is not, would not be using exactly the same arguments because you apply an SVE to a geodesic ray or quasi-geodesic ray, it ends up being a set of points that is no longer a geodesic ray or quasi-geodesic ray. So it's a set with some properties. And also because of the first bulletin point that induce a homeomorphism between the boundaries. So if the boundaries are not the same, then the groups are not SVE equivalent. The corollary would say a finite generator hyperbolic, I guess some problems is SVE to a free group if and only if it is virtually free. And SVE to a subsurface group if and only if it acts on a hyperbolic plane. These are things you can distinguish by the boundary.
I think Gromov showed that.
The first one?
Yeah.
Okay. Thank you. And there are more things such as for finitely generated groups, sub-exponential growth is an SVE invariant property. And Qing and his collaborators, they mentioned that Morse qualified an SVE invariant. So there are interesting, so the goal would be what are the other properties that are SVE invariant? So we did that for the sublinear Morse boundary. To say that at phi and theta SVE, theta being the additive error, between two properties that is spaces x and y. And suppose it is dominated by kappa. In the usual sense, the function is dominated by another function. Then theta induce a homeomorphism between the kappa boundaries. So two finitely generated groups have non-homeomorphic kappa boundaries, then they are not SVE. So how do we prove that? Or how do we go about it? It turns out there's one more level of sublinearification we can do. And it turned out to be equivalent definition from the first one. So let's see the definition first. We can also say a quasi-geodesic ray gamma is kappa Morse if there exists a gauge function, a family of gauges, such that for any other or any sublinear function kappa prime, and for any small r greater than 0, there exists a large R such that for any segment alpha, such that if at this much later time, alpha and kappa prime close to gamma, then in the initial time, in the initial radius R, and alpha is within the correct gauge, is in the gauge of gamma. So what this says is that it doesn't have to be a segment that starts and ends on gamma. It has to, it can just end sublinearly close to gamma. Even that is enough. So, and that is precisely the game that we play in this proof, because when I have a geodesic ray, I map it by SVU to space Y. Now it's becoming some set. It's okay to say a set is kappa Morse. That definition itself doesn't require anything. But now I want to study another quasi-geodesic ray that is in the sublinear, is kappa close to it. So I pull it back by the SV inverse. Now that object becomes some kind of a set of points that is sublinearly close to my original quasi-geodesic. So I started to consider the most usual method, points from origin to some points on the set. These are all geodesic segments, and look at them and take a limit to them, and I realized these things are sublinear, are quasi-geodesic ray whose endpoints are sublinearly close to my original object. And by this argument, that is in fact good enough. Okay. So one application we can say is that you can use this to attempt to understand asymptotic forms of right angle constants, or FB equivalent to right angle constants. Let G be a simplicial graph on a set of elements, and we use this graph to define a right angle constant group by saying every element, every vertex represents an element of order 2, and every edge represents a commuting function. So this would be A, B, C, D, where A squared plus B squared plus C squared plus D squared because of order 2, and AB commute. Now this is maybe 2. AB the A's. Anyways, so all the edges commuting. Okay. So if G is a complete graph on the set of vertices, then the group is Z mod to Z, direct product encompasses direct product. On the other hand, if G has no edges at all, then it's a free dot of a bunch of order 2 elements. Okay. So now I want to distinguish 2 right angle cluster groups whose asymptotic or whose FB equivalence is not so clear otherwise. And this is a famous example exhibited by Beerstock to test or to contradict, to test a bunch of statements. It involves a lot of the A1, A2, B1, B2, that you can think of them as staining a flat, and then many flats linked together. But then you have a pentagon that connects some of these such that it gives you a combinatorially embedded hyperbolic plane. And that plane, it's Morse boundary, but also sublinear Morse boundary, would have a circle in it, while without, we would see the Morse boundary and the sublinear Morse boundary being totally connected, or totally disconnected set. Therefore, if we want to ask, are these 2 groups have sublinearly Bilipschitz equivalent? Seems hard, but one sufficient condition is to say they're definitely not, because their boundaries are not homeomorphic. And this doesn't help us directly rule out that their asymptotic cones are bilipschitz equivalent. SPE would imply that, but not SPE, we don't know for sure. But the asymptotic cones are difficult to compute as well. Okay, so I think I went a little too fast. So there's some other properties of the sublinear Morse boundaries of zero spaces, and some of this hopefully is also true in general. The first, as expected, is also a visibility that given any 2 points and in the boundary there exists a geodesic line that connects that limits to both of these points that go through the space.
You know, this is like geodesic line, like sublinearly Morse.
Yes, it has to be because it eventually will go into the neighborhood of both of them. Yeah. If you have 3 of these, the classical thing is for Gromov boundary is for any 3 points you would be able to locate with bounded error of points in the middle of the space. To move that argument over here, you wouldn't be able. It would be sublinear error. You would have the center of the triangle somewhere with sublinear error. So pretty much the same method, and then for also maybe as expected, the action of the group on the boundary is dense. So for each element of the sublinear Morse boundary, the G.A is dense in the whole boundary. And also maybe expected that these, if you adjust the divergence definition a little bit to suit the situation, then there will be as expected superlinear in diversion. Okay, I think that's it actually. So let me end on this.